This video describes the process of sizing linear and PWM amplifiers driving a linear brushless motor. A typical motion control system is represented by this block diagram. There's a motion controller that commands a position profile x of t, which implicitly defines a velocity profile v of t. This motion is assumed to be periodic. That is, once completed, the motion repeats itself. We use the velocity profile in the amplifier sizing process. There's a Varidan linear or PWM amplifier that produces phase currents that drive the linear brushless motor and load. Our goal is to determine the amplifier requirements given the velocity profile and the motor and load parameters. The needed motor and load parameters are motor force constant, expressed in newtons per amp RMS, for example, the motor phase-to-phase back EMF constant, K sub E, often expressed in V peak phase-to-phase, radians per second, the phase-to-phase resistance R, the phase-to-phase inductance L, the motor pitch P in meters, and the motor load mass in kilograms. The spreadsheet gives us some alternatives for the choice of units, but we have to be very careful to make sure that we're expressing the units appropriately. With these design inputs, we can compute 5 design outputs that are used at Varidan to help choose an amplifier for your application. The design outputs are the amplifier bus voltages. In the case of a linear amplifier, those bus voltages are plus minus B, so that the voltage between the two buses are 2B, or the rail-to-rail voltage is 2B. In the case of a PWM amp, we use a single bus voltage 2B and a ground return. So we use this parameter B in both cases to be consistent with our calculations, and again, in both cases, the rail-to-rail voltage is 2B. The peak output current, I peak, the continuous output current, I continuous, and for linear amplifiers only, we need to compute 2 additional specifications. Those are peak output power and continuous power dissipation, and we've noted those with an asterisk, and we use the same notation in the corresponding application note to indicate that these calculations apply to linear amplifiers only. In the case of PWM amplifiers, the peak and continuous power dissipation in the drive transistors can be calculated from the peak output current and the continuous output current alone, so that we need fewer parameters in the sizing process. So let's do an example. The design inputs, again, are the force constant. In this case, we're choosing that to be 39 newtons per amp RMS. The back EMF constant, 32 volts per meter per second. The phase-to-phase resistance, the phase-to-phase inductance, the motor pitch, and the total moving mass, both internal and external, to the linear motor. So again, we want to be very careful with the units. And we're choosing a velocity profile that's trapezoidal. This allows for a simple description, and most of the time we can do a good job sizing with a simple worst case trapezoidal velocity profile. We recognize that often that these profiles will be rounded with S-curves and so forth, but that will ensure that you're well within the safe operating area of the amplifiers. So the trapezoidal profile is easily transcribed into a Excel sheet by noting the vertices of the profile. So the data points that we need to transcribe are the corners, so 0 seconds at 0 meters per second, 50 milliseconds at 1 meter per second, 450 milliseconds at 1 meter per second, and so forth, all the way up to 1800 milliseconds at 0 meters per second. Here is the linear brushless motor spreadsheet available from the Viridin website, where we can size linear and PWM amplifiers. The spreadsheet is color-coded. Blue indicates design inputs that we must supply. We fill in the blue cells with the heavy boundary. And the green indicates the design outputs, which are the amplifier requirements. First, we enter the motor parameters in units. For example, the force constant, we're showing here newtons per amp RMS like we showed on the last slide, but there's some options. Millinewtons per amp RMS, pounds force, ounce force, and so forth. Likewise, for the back EMF constant, we normally use volts per meter per second, but there are some other options here. So we can just we can select those. We just got to be sure that we're consistent with the value that we're inputting. The resistance and inductance are always in ohms and henries. So the 18 millihenries that we had on the last slide gets converted to 0.018 henries, of course. The motor pitch we're showing in meters, but there's options. Likewise, the mass has some options. We're using kilograms. So I've already input the values from the last slide. The other data we need are the 9 corner points of the trapezoidal velocity profile. So again, we choose units. We're using meters per second. And the corner points were at 0 seconds, 50 milliseconds, 450 milliseconds, and so forth, all the way up to 1800 milliseconds. And so we're expressing those quantities in seconds. And the velocities were 0, 1, 1, 0, 0, minus 1, minus 1, 0, 0 meters per second for the corners. So we input those numbers. The spreadsheet automatically computes B that defines the bus voltages. So here we're showing 71.8 volts. We've selected a margin to deal with uncertainty. So we're free to set that to 0 if we're very confident that our power supply voltage won't have any drops and so forth. We typically use, say, 20%. And so the voltage for a linear amplifier would be plus minus 71.8 volts on the buses. For a PWM amplifier, the bus voltage would be twice that, and the return would be on a ground. The other parameters are the peak power. Again, we only need that number for sizing a linear amplifier, so we indicate that with an asterisk. The peak current, the continuous current, and the continuous power for linear amplifiers, again indicated by the asterisk. So put in your parameters, your worst case velocity profile, and send this spreadsheet into sales@viridin.com, and we can help you choose an amplifier.